Guten Morgen und herzlich willkommen zum swisstopo Kolloquium. Ich freue mich sehr, heute 3 Gäste hier begrüßen zu dürfen. Das sind Lorenz Hurni, Yisi Chen und Sidi Wu von der ETH Zurich. Und per Video werden wir auch noch 2 Beiträge sehen, die ebenfalls aus dem Team Hurni stammen, und zwar von Zhenjing Xiao und Jue Jia. Und alle diese Beiträge und die Forschung aller unserer Gäste dreht sich um ein zentrales Thema, und zwar ist es die Digitalisierung von historischen Karten. Und weil dabei die Siegfried-Karte, ein historisches Produkt aus unserem Haus von swisstopo, eine zentrale Rolle spielt, werden Sie heute auch Ihre Forschungsprojekte bei uns präsentieren. Lorenz, Yisi, Sidi, vielen Dank, dass ihr hier seid. Wir freuen uns sehr. Und zum Abschluss, bevor ich übergebe, noch einen Hinweis für alle, die das hier oder zu Hause anschauen. Ein Teil der Vorträge wird auf Englisch sein, wie in der Ankündigung angemerkt. Gut, Lorenz, go ahead.
Ja, vielen Dank, liebe Fred. Danke auch für die Einladung hier. Es geht also heute um die Digitalisierung von historischen Karten, ein Schwerpunkt unserer Aktivitäten in den letzten Jahren. Und ich werde unterstützt von einem ganzen Team, wie das schon angekündigt wurde. Ich werde den ersten Vortrag, der ein bisschen die Übersicht gibt, auf Deutsch halten, und dann werden die weiteren Beiträge auf Englisch dann präsentiert. Ja, also zuerst ETH Zurich. Wir sind ja an der ETH Zurich beheimatet, da sage ich nicht allzu viel dazu, das ist ja wahrscheinlich bekannt. Technische Hochschule in 1855 gegründet und sind doch etwa 30.000 Mitarbeitende, respektive Angehörige, inklusive Studierende, also eine kleine Stadt im Prinzip, die da in Zürich integriert ist. Wir sind allerdings nicht in diesem schönen alten Hauptgebäude, sondern auf dem Campus Hönckeberg. Und da kann ich gleich mal auf swisstopo-Bilder, historische Bilder zurückgreifen. Hier ein Luftbild von 1932, da befindet sich heute eben der Campus Hönckeberg. Da war hier noch grüne Wiese, noch nicht viel vorhanden, außer dem allerersten Radiosender der Schweiz. Der war hier auf dem Hönckeberg angesiedelt. Man sieht ihn auch noch irgendwo, die Masten, noch vor Beromünster, aber es hat dann in den 60er Jahren begonnen, hier mit dem Bau dieses Campus. Das kann ich schnell durchgehen. Dann in den 80er Jahren, als ich studiert habe, ist das schon gewachsen. Dann mittlerweile auch die farbigen Luftbilder, 2007, 2013 und dann das jüngste Bild 2022. Also das ist ein wunderbarer Datenschatz bereits, den wir auch verwenden können für unsere Arbeit. Wir beschäftigen uns allerdings eher dann mit solchen Daten. Das wäre unser Ziel, dass wir so wie beim TLM hier am Schluss Vektordaten verwenden können für unsere Arbeiten. Ja, das Institut selber ist 1925 gegründet worden und man kann das jetzt einfach ausrechnen, 100 Jahre ist das her jetzt, dass das von Eduard Imhoff gegründet wurde. Es gibt heute 2 Lehrstühle oder Professuren, Kartografie, also der meinige, und dann Geoinformation Engineering von Martin Raubal. Und unsere Studierenden sind hauptsächlich Geomatik-Ingenieurinnen und Ingenieure, die wir einfach mit den modernsten Methoden der Datenverarbeitung in diesem Bereich, Visualisierung und so weiter, ausrüsten möchten. Das ist übrigens noch der Stammbaum dieser Professoren. Begonnen hat es mit Johannes Wild, das war so eine One-Man-Show, damals 1855. Und das hat sich dann aber schnell so in einen Geodäsie und dann schlussendlich GIS-Ast aufgesplittet und in einen Kartografie-Ast oben mit Fridolin Becker, dann Eduard Imhoff, dem Institutgründer N. Spiess, und mir und Martin dann heute. Ja, ich habe es angedeutet, 100 Jahre, wir sind deshalb auch in die Archive gegangen bei uns im Institut. Das ist leider nicht alles so schön sortiert und indexiert wie hier in der swisstopo. sondern etwas ungeordnet und haben mal in diesen Schätzen gegraben. Und was dann rausgekommen ist, ist diese Festschrift zum 100-jährigen Jubiläum, die im Moment gerade in den Druck geht. Da haben wir eigentlich diese verschiedenen Professuren seit 1855 sogar verfolgt und dokumentiert, was da eigentlich die Hauptsache in der Forschung und in der Lehre war und dann sehr reich illustriert mit diesen Schätzen aus dem Archiv. Ja, und was ich hier gleich ankündigen kann, wir werden nicht nur eine Festschrift herausgeben, sondern am 4. und 5. September gibt es dann ein Kolloquium, ein Symposium bei uns in Zürich, wo Sie alle auch ganz herzlich eingeladen sind. Doch jetzt etwas näher zu unseren Forschungsaktivitäten, was wir also in unserer Professur hier machen. Ich gehe nicht auf alles ein, was ich da gelb markiert habe, da werde ich kurz ein paar Beispiele zeigen. Topografische Kartierung, Methoden zur topografischen Kartierung und Darstellung, insbesondere Geländedarstellung ist so ein Schwerpunkt. Dann auch Geoportale in den letzten Jahren und dann natürlich eben die historischen Karten, auf die wir heute dann näher eingehen werden. Interaktive Atlanten, wie der Atlas der Schweiz, aber auch der gedruckte Atlas, der Schweizer Weltatlas. Da sage ich kurz noch etwas dazu. Ja, hier, das ist auch schon fast wieder historisch, das war ein Kartenbeispiel, das ich im Rahmen meiner Dissertation in den 90er Jahren am Institut erstellt habe. Das war eine vollständige Vektordarstellung. Im Hintergrund sind also alles Vektordaten. Das war damals eigentlich neu, dass man wirklich die ganze Karte, was heute selbstverständlich ist, in Vektoren aufbaut. Und wir haben uns dann nicht für ein Schweizer Gebiet entschieden, sondern für ein Gebiet in Griechenland und haben daraus diese topografische Karte mit Bodenbedeckung und auch diese geologische Karte dann abgeleitet. Und die Feldarbeit habe ich seinerzeit also aus Luftbildern und im Feld gemacht. Und das hat dann damals so ausgesehen, die Bearbeitung, damals noch am Intergraph-System in den frühen 90er Jahren. Und swisstopo hat mich dann abgeworben und ich war dann hier im Hause zuständig seinerzeit für diese erste Digitalisierungsgeneration, also nach Cytex dann dieses System, das da mit der Software Trinuage betrieben wurde. Da konnte ich mitarbeiten, das da einzuführen. Ja, dann weitere Schwerpunkte, eben der Atlas der Schweiz, der thematische Nationalatlas, wo wir sehr viele Themen, insbesondere auch aus wissenschaftlichen Projekten, präsentieren und auf eine 3D-Umgebung hier zur Verfügung stellen, online. Im Moment sind wir daran, das auf eine voll webbasierte Version umzustellen. Und hier der Schweizer Weltatlas, der Schulatlas, also noch in gedruckter Form. Er wird dann Ende 26, Anfang 27 in einer revidierten Version erscheinen und damit verbunden dann auch eine interaktive Version ist geplant. Und ab und zu schafft man es dann noch in die internationale Geopolitik damit, wenn dann ein Präsident in den USA eine Ortsbezeichnung umbenennen will, hier Gulf of America und Gulf of Mexico, dann habe ich mich dann geäußert, dass wir das im Schulatlas nicht tun werden, sondern den bisherigen Namen beibehalten. Und die Presse hat das dann natürlich sehr gerne aufgenommen mit allen Kommentaren, die hauptsächlich positiv sind dann zu diesem Entscheid. Also zu meinem, nicht zu dem vom Präsidenten. Ja, eben ein weiterer Schwerpunkt Geoportale und da kommen wir jetzt schon etwas näher diesen historischen Karten, weil das war eigentlich der Auslöser hier. In der Wissenschaft gibt es natürlich wie auch in Ingenieurbüros oder den Anwendern von swisstopo-Daten sehr viele Bedürfnisse eben nach Geodaten, Höhendaten, Netzwerkdaten, Grenzen, Toponyme, Bodenbedeckungen und so weiter. Und das hat uns dann eigentlich in den Nullerjahren dazu geführt, dass wir ein eigenes Geoportal aufgebaut haben. Swisstopo hat es damals noch nicht zur Verfügung gehabt, also man hat die Daten quasi per Disk erhalten. Heute ist es natürlich anders, man kann die Daten runterladen, aber die Idee damals war eigentlich der Wissenschaft, zunächst mal der ETH ein Portal zur Verfügung zu stellen, wo man Geodaten einfach nicht nur fileweise runterladen kann, sondern sie wirklich auch live anschauen kann, einen Ausschnitt definieren über eine Box oder auch über Koordinaten und dann diesen Ausschnitt herunterladen. Das hat dann zu diesem GeoVid-Portal geführt, dann in verschiedenen Ausbaustufen. Heute sieht das so aus, die aktuellste Version Wir sind daran, dieses Portal jetzt nicht nur für die Wissenschaft zu öffnen, sondern quasi auch mit offenen Daten, auch offen für das gesamte Publikum zur Verfügung zu stellen. Und zwar nicht nur mit swisstopo-Daten, wie wir sie hier haben, sondern eben auch zur Verfügung zu stellen, um wissenschaftliche Daten, die Forschergruppen freigeben, dass man die dort publizieren und andere sie auch herunterladen und verwenden können. Und eine der Anforderungen eben der Wissenschaftler war eben, dass sie gesagt haben, ja, ihr habt diese schönen Scans, beispielsweise der Siegfried-Karte, und man sieht es hier auch links oben, alle Zeitstände sind auch entsprechend verfügbar auf diesem Portal. Das ist ja schön, wenn ihr die gescannt verfügbar habt und man die runterladen kann, aber was ich eigentlich will, sind Vektordaten von diesen historischen Daten. Und das hat dann eigentlich dazu geführt, dass wir eine Reihe von Projekten gestartet haben, um historische Karten zu vektorisieren, mit Hilfe jetzt natürlich neuerdings von Methoden, mit KI-Methoden oder Deep Learning-Methoden, solche Daten zu erzeugen. Da gibt es einen großen Forschungsbedarf natürlich, das kann man nicht einfach so machen und das ist das, was wir eigentlich heute präsentieren möchten. Wir haben uns natürlich hauptsächlich mal auf die Siegfried-Karte und auch die alte Landeskarte gestützt als historische Daten und haben das dann mal gestartet, so ungefähr 2018 ist das losgegangen. Und so die Grundidee dahinter sind eigentlich von der Methodik her, sind eigentlich Filteroperationen. Also Sie kennen vielleicht diese klassischen Filteroperationen links oben, wo ich einfach einen Ausgangspixel nehme, etwas mache, eventuell auch die Nachbarschaft dieses Pixels einbeziehe und dann einen Output-Pixel erhalte. Und das Beispiel links oben wäre so ein Mean-Filter, also so ein Mittelwertfilter, wo ich einfach das Pixel nehme in der Mitte und dann noch die Nachbarschaftspixel nehme und dann quasi den Durchschnitt berechne und dann erhalte ich im Prinzip einfach ein geglättetes Bild. Das macht jetzt vielleicht in diesem Beispiel nicht so Sinn, aber das wäre eine einfache Filteroperation. Eine andere Operation wäre eine Kantendetektion, wo ich eben das zentrale Pixel gewichte und dann die Pixel ringsherum negativ gewichte und dann erhalte ich quasi nur noch die Kanten dieser Objekte und könnte die dann vektorisieren. Allerdings ist das jetzt etwas komplizierter, wenn ich also jetzt aus dieser Siegfried-Karte links nur die Häuser herausholen möchte, die Straßen interessieren mich nicht, dann finde ich nicht einfach einen Filter, der dieses Problem löst, sondern das müsste dann wahrscheinlich eine Reihe von Filteroperationen sein, die ich hintereinander schalte, um dann zu diesem Bild rechts zu gelangen. Das ist immer noch ein Pixelbild, aber Sie sehen, das kann ich dann einfacher vektorisieren, wenn ich das Bild so, die Häuser separiert habe. Und so eine klassische Methode ist eben diese U-Net-Architecture, also ein neuronales Netz, das ich entsprechend verwende. Und man sieht dann, ich habe dann links wieder die Siegfried-Karte und rechts dann dieses gewünschte Output-Bild, das ich hier habe. Und dann muss ich also eine Reihe von Filtern finden, die mir dann dieses Bild umwandeln in das Zielbild hier. Und im Prinzip ist es so eine Art Try and Error, die auf clevere Art und Weise gemacht wird, weil es werden im Prinzip dann Musterbilder links und Zielbilder rechts, die ich erzeugt habe zum Trainieren, also die muss ich vielleicht sogar von Hand digitalisieren, wenn ich genügend von diesen Zielbildern habe und die dann kopple ich die dann quasi mit dem Ausgangsbild und finde dann durch ein iteratives Verfahren in der Mitte diese Reihe von Filtern, die ich anwenden muss, um zum Zielbild zu kommen. Und da gibt es dann verschiedene Operationen, zum Beispiel Pooling, wo ich dann gewisse fehlende oder gewisse Feinelemente weglasse, das Bild zum Beispiel auch reduziere im Umfang und so weiter. Und da gibt es eine ganze Reihe von iterativen Verfahren, wie ich dann zu dieser Funktion komme, um dieses Ausgangsbild ins Zielbild zu verwandeln. Wir werden davon dann noch mehr hören in diesen detaillierteren Vorträgen. Aber das war so dieses U-Net, mit dem hat es eigentlich begonnen. Und das Bild wurde dann so in Kacheln aufgegliedert und dann Kachel für Kachel abgearbeitet. Man sieht, dass man auch noch in der grüne Rahmen, dass man die Nachbarschaftskacheln auch noch mit einbezogen hat, dass es nicht irgendwelche Artefakte, Elemente an den Rändern gibt. Und das wäre jetzt so ein Resultat hier, immer noch quasi im Rastermodus, also diese Bilder, also diese Häuser quasi aus dem Bild extrahiert. Der nächste Schritt wäre dann die Vektorisierung. Da brauche ich nicht groß drauf einzugehen. Das ist etwas, was Sie ja, im GIS eigentlich standardmäßig auch machen können. Hier hat man dann einfach die Pixel verfolgt, die roten Pixel, die detektiert wurden. Und wenn dann der Winkel geändert hat an einer Ecke, hat man diese Winkeländerung da auf dieser Grafik aufgezeichnet. Und wenn die groß genug war, war man sich sicher, dass dort eben eine Ecke ist und konnte dann auch die Ecken definieren. Hat dann rohe Vektoren links erhalten, konnte die allenfalls noch rektifizieren, also rechtwinklig behalten. Das wäre auch eine GIS-Funktion, damit es dann nach sauberen, rechteckigen Häusern aussieht, unter gewissen Schwellwerten, die da einbehalten werden. Und allenfalls musste man noch etwas manuell dann korrigieren. Also beispielsweise das Bild, das Haus, das orange Haus unten in der Mitte, das war dann eben effektiv nicht rechtwinklig, sondern es hatte so einen Spitzenwinkel, was man da auf der rechten Seite jetzt sieht, das wurde dann auch noch manuell korrigiert. Und von der Siegfried-Karte konnten wir so dann eigentlich alle Stände mit etwa 6 Millionen Features, also jetzt nur die Häuser, so digitalisieren. Und die stehen jetzt auch zum Beispiel auf dieser GeoVid-Plattform zur Verfügung und können heruntergeladen werden. Aber da gibt es natürlich noch viel zu tun. Da müsste man sicherlich noch weiter bereinigen. Auch natürlich das Matching mit den heutigen Geodaten, Generalisierungseffekte, die man vielleicht dann wieder beheben möchte, das müsste man jetzt noch weiter machen daran. Dasselbe dann für die Ortsnamen, auch da haben wir ein Verfahren, wie wir Ortsnamen dann aus solchen Siegfried-Karten herausholen können. Und das hat dann zu einer ganzen Reihe von Fortsetzungsprojekten geführt. Die zwei, die eigentlich auch heute dann noch vorgestellt werden, ist dieses Historical River Change. Das war dann mit Kollegen von der EAWAG zusammen. Die waren interessiert eigentlich an den Flussnetzen, wie man die herausholen kann aus diesen Bildern, weil sie wissen wollten, wie die Flussnetze früher verliefen. Und das ist interessant zum Beispiel dann für Renaturierungen von Flussnetzen in der heutigen Zeit. Da wäre es interessant zu wissen, wie das früher war, dass man das vielleicht wieder rekonstruieren kann. Und das zweite war dann das Emphasis Project. Da geht es dann eigentlich eher so um Ökosysteme, wie die vernetzt sind, wie die früher vernetzt waren. Da geht es dann auch um Siedlungsgebiete, die man herausholt, dann vielleicht auch Straßen, die Siedlungsgebiete und Ökosysteme zerschneiden. Und das ist ein Projekt zusammen mit den Planern an der ETH. Das sind dann so ein paar Beispiele. Hier haben wir eben diese Gewässernetze herausgeholt aus der Siegfried-Karte. Wir konnten sogar ein Gewässernetz vollständig rekonstruieren, 1870 im Vektormodus, mit allen Topologien, die dann bereinigt waren. Und da sieht man jetzt den Ablauf hier. Hier links eben die Inputdaten, rechts das könnten Outputdaten sein oder eben auch Trainingsdaten, die wir erzeugt haben, um diese Netzwerke zu trainieren, diese Funktion also zu bestimmen. Und dann wird diese Segmentierung dann aufgrund dieser Trainingsdaten und dieses Modells erfolgen. Und ich erhalte dann solche Rasterflächen dieser aufgeteilten Gewässer, also Flüsse, Bäche, Seen und auch Wetlands, also Sumpfgebiete mit diesen horizontalen Strichen. Das konnte man so herausholen. Das sieht man hier noch einmal jetzt am Beispiel in grün der Sumpfgebiete, blau die Flüsse und dann rot werden dann noch die Bäche. Und wenn man das dann bereinigt hat, sieht es so aus, vektorisiert auf der rechten Seite. Und man sieht dann bei diesem Bach, da wurde einfach eine etwas verdickte Linie, wurde dann als kleiner See interpretiert. Das ist aber nicht richtig. Man sieht es dann im Vektormodus, haben wir das dann noch von Hand korrigiert, weil es war dann eigentlich eine Aufsplittung dieses Baches, nicht ein See oder ein Tümpel. Und solche Dinge musste man dann unter Umständen von Hand noch korrigieren. Aber der Aufwand da hält sich dann in Grenzen, wie viel man effektiv noch machen muss von Hand. Es gibt natürlich dann viele Spezialfälle, insbesondere Signaturen, die nicht immer gleich gehandhabt werden oder nur einmal auftreten, wie diese Stützmauer da beim Einfluss eines Flusses in einen See, oder dann auch Scan-Artefakte, solche Farbsäume, unklare Objekte mit diesen Schraffen hier und Überlagerungen von Straßen, von Elementen übereinander. Das sind dann alle diese Dinge, die die Maschine dann nicht so einfach handhaben kann und man dann unter Umständen spezielle Lösungen oder auch manuell dahinter gehen muss. Also das war jetzt eigentlich ganz kurz die Einführung, was wir so tun, und ich kann hier ganz kurz vorstellen, was jetzt die nächsten Präsentationen sind. Der erste Beitrag wäre von Chenjing Zhao. Sie hat dann eigentlich quasi diese ersten Arbeiten fortgeführt in ihrer Dissertation und hat sich dann insbesondere dann um Straßennetze gekümmert, die sie aus historischen Straßenkarten oder Siegfried-Karten herausgefiltert hat. Und dort insbesondere ist sie auch eingegangen auf spezielle kartografische Symboliken, Symbologien, Zeichenschlüssel, die sie dann mit definiert hat, damit das eben einfacher erkennbar war. Der zweite Beitrag wird dann von Sidi Wu sein. Sie wird dann über ihre Arbeiten im Rahmen eben dieses Historich-Projekts auch berichten. Das übrigens, Chenjing ist nicht mehr bei uns. Sie hat dann einen Video geliefert, den wir dann gleich abspielen werden. Sidi ist heute da und Xue ist auch im Moment nicht da. Sie ist in den USA in einem Forschungsaustausch und wird dann über Zeitreihen berichten, die man aus Karten herausholen kann. Auch das wird ab Video dann gezeigt. Und am Schluss Easy Chen wird dann noch auch über weitere Arbeiten berichten, wie man beispielsweise auch historische Daten aus Karten verlinken kann mit weiteren Informationen. Und dann würde ich jetzt mal überleiten zu dieser Präsentation hier. Und da müsste ich jetzt diesen eingebetteten Video starten können. Ich weiß nicht, wer das machen kann. Weiterdrücken.
Hello everyone, I'm Chenjing Jiao. I'm a doctoral student from the cartography chair of ETH Zurich. I would like to present to you what I have been mainly working on during my PhD. The title of my presentation is Extracting Road Features from Historical Maps by Incorporating Cartographic Method Knowledge into Deep Learning. This is the table of contents of this presentation. First, I did a literature review of road extraction methods. Through this literature review, I identified research gaps and research questions. And the following three methods are developed to tackle the research questions. In order to develop road extraction methods from historical maps, it makes good sense to review existing methods. Here we broaden the data source to raster maps and overhead imagery, because road extraction methods from these data sources will possibly benefit the development of methods from historical maps. There exist already various techniques like morphological operations, color image segmentation, line tracing methods, and so on. We categorize these existing techniques into three groups, namely line extraction, image filtering, and color image segmentation. Through the literature review, we found that there exists only limited amounts of studies that use deep learning-based methods for road extraction from historical maps. More importantly, there exists no study that employs cartographic method knowledge to enhance deep learning-based road extraction. Here, cartographic method knowledge refers to something like symbolization rules, color usage, generalization method, and so on. To tackle these research gaps, we formulate the following 3 research questions. In research question 2, we will explore how cartographic method knowledge can be used to augment the training dataset for road extraction. In research question 3, we go one step further. We examine how cartographic method knowledge can be employed to automatically create training data. In research question 4, we will use cartographic method knowledge to vectorize and to classify the road extraction results. We have only a limited amount of training data for road extraction. An intuitive solution to boost the training dataset is data augmentation. In conventional data augmentation methods, usually the image patch or the training sample will be transformed as a whole. Here is an example of rotating the input image on the left by 180 degrees, and on the right we see the result. But we see something strange because all the labels, the height numbers, the triangulation point are totally upside down. Actually, this would never appear in practical cases. So here, cartographic method knowledge tells us which features can be transformed and which features cannot. Our solution to this issue is a novel data augmentation method in which only the target features will be transformed instead of the whole training sample. Here our target feature is road feature. On the left is an example of rotating road areas by 90 degrees. So here we see only the black lines are rotated. The background, the brown lines representing other lines remain unchanged. On the right is another example of flipping the roads horizontally. So again, only the black lines are flipped. The label, the background, the other lines remain unchanged. As I mentioned, we have a small amount of training data. They are the road center lines that cover the Zurich city of the year 1940. Here, the red lines represent the road center lines. These center lines are buffered according to road widths, and the buffer are then rasterized so that they can be fed into a deep learning model for training. We use UNet for training, which is a classical convolutional neural network that appears in a more or less symmetrical shape. It consists of a contracting path and an expansive path. To evaluate the road segmentation results in raster format, we use a matrix accuracy and F1 score. The raster road segmentations can be vectorized by using existing methods like morphological operations and vectorization tools in ArcGIS. And to evaluate the vectorization results, we use correctness and completeness. Here are the qualitative results. On the left, the original map images and the corresponding ground truth. On the right, the road extraction results without data augmentation method, with conventional data augmentation method, and with the novel data augmentation method. The results with the novel method look more robust. The connectivity of road areas looks better than results from other methods. In this table lists the quantitative road extraction results. We see the matrix values of the novel data augmentation method outperform those from the other method. As we all know, one main obstacle of employing deep learning is a high demand of large amounts of training data, and usually it's so tedious and so time-consuming to manually label the training data. So in research question 3, we will use cartographic simplification knowledge to automatically create training data for road extraction. Our solution is, first we reconstruct the symbols on historical maps, and then we apply the reconstructed symbols to the contemporary geospatial data. Because in the contemporary vector dataset, we already know the label of each feature. For example, we know this line is a road, that polygon is a building, and so on. On the left are the symbols on the black layer of the Swiss Siegfried map. Here we narrow down our scope to the black layer because all root features are contained in the black layer. And we reconstructed the symbols by using the symbol editing tool in ArcGIS. So on the right, we see the reconstructed symbols. Above here, the 6 root symbols, and below here, other symbols from the black layer. For example, buildings, railway, triangulation point, label and elevation number, administrative borders, and so on. Regarding the contemporary geospatial data, we adopt the Swiss TRM3D dataset, which is a large-scale, comprehensive vector dataset that covers the whole Switzerland. We symbolize the features in Swiss TRM3D dataset with the corresponding reconstructed symbols. On the right, we see the results. It really mimics the Siegfried map, and we name it the imitation map. The imitation map is exported into raster format, and each imitation map sheet has exactly the same spatial extent with the corresponding Siegfried map sheet. And the imitation map has the same spatial resolution with the Siegfried map. So it means that the imitation map can be trained alone or can be trained together with the Siegfried map. And again, the real training data we have are still the road center lines of Zurich city. These real training data are also buffered and rasterized, and we still train with UNet. In order to compare the performance of training with only the real map, training with only the imitation map, and training with mixed Siegfried map and imitation maps, we developed the 3 training scenarios or these 4 training cases. In training case 1A, we train on the original Siegfried map. In 1B, we train on the black layer of the Siegfried map. By comparing 1A and 1B, we will see the impact of adopting the color usage information on the performance of road extraction. In scenario 2, we train with only the imitation maps, and in scenario 3, we train with real Siegfried map and imitation maps in combination. In order to examine the impact of different number of training samples on the performance, we tried to vary the numbers, namely 20,000, 10,000, and 5,000. And the raster road segmentation results can be vectorized by using morphological operations and the vectorization tool in ArcGIS. Here are the qualitative results. The blue lines represent the extracted road center lines. On the left, we see the original map images and the corresponding ground truth. And on the right, we see the results from the 4 training cases. Generally, results from the 4 cases look already good. In result 2, which are obtained by training on the imitation maps only, sometimes the parallel road lines are extracted instead of the road center line, and there exists some false positive around the label. But these issues can be largely solved by combining the real and the imitation map as shown in result 3. In this table, we see the quantitative results. Generally, with the numbers of training samples increasing, the matrix values go increasingly better. Surprisingly, the matrix values from result 2, which is obtained by training only on the imitation map, look already satisfactory. And by combining the imitation map and the real map, the matrix values go far better. Notably, the correctness value from result 3 outperforms those from result 1A and 1B, which are obtained by training on the real map. In research question 2 and research question 3, we vectorized the extracted road areas by using morphological operations and the vectorization tool in ArcGIS. Here is an example of the results. The blue lines show the vectorized road center lines, but these lines follow a zigzag issue and these lines are not classified. So in research question 4, we will utilize cartographic symbolization knowledge for road vectorization and road classification. Our solution is, first, we define a painting function for each road class because each road class is represented by a distinguished road symbol. And we use the painting functions to paint a road segment. Then we compare the painted road segment with its correspondence on the historical map. The symbol that achieves the minimal loss is used to label the class of this segment. Here is the workflow. It consists of 3 blocks: segmentation, skeleton analysis, and painting. First, we use deep learning to get road segmentations in raster format. Then we use connected component analysis and morphological operations in order to get road skeletons. The skeletons cover the whole map sheet, and it is clipped into small patches sized 128 times 128 pixels. In each patch, we again use connected component analysis to get each connected curve. Then we use curve decomposition to find the start point, end point, and the intersection points for each curve. Then for each single curve, we apply Douglas-Pilker algorithm to find the key points or the turning points. Now we see each segment between the 2 points identified by Douglas-Pilker algorithm and curve decomposition is more or less straight. As long as we get a straight segment, it can be painted by each of the 5 road symbols. And then we compare the painted result with the target on the black layer of the Siegfried map. A loss is computed. The symbol that achieves the minimum loss is used to identify the class of the road segment. Here is an example of one of the painted results. On the left, the black layer, on the right, the painted roads. Generally, all road segments can be correctly painted. On the right, we see the vectorization results from the conventional methods versus the vectorization and classification results from this novel painting method. Again, road lines from the conventional method follow this sawtooth issue, but all road lines vectorized by this painting method are all straight, and they are already classified. Here is small road vectorization and classification results. Class 1 is represented by single dashed line. We see an example here. Class 2, single solid line like we see here. Class 3 is symbolized as a solid line together with a dashed line. Class 4, 2 parallel lines. Class 5, 1 thin line in combination with a thicker line. So generally, all roads can be correctly classified. From this table, we see the quantitative result. The matrix values look generally good, but you may notice that the correctness value for road class 1 is not so good because it's challenging to distinguish single dashed line from single solid line. So some class 1 roads are misclassified as road class 2. That's all of my presentation. Thank you for your time, and all questions are very welcome.
Okay, so far for the presentation. Thank you very much. 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 Thank you very much and I hand over to CD Wu now, giving her second talk.
Oh, the template is different than what I gave you.
Sorry?
I think the template is different than what I give you, but it's okay, yeah.
Just.
Okay. So, hello everyone. Welcome to my presentation, Mapping Through Time, Reconstructing the Mapped Past and Shaping the Future of Cartography with AI and VR. Today, I will give you a small journey from the past to present. So, from the past, I will introduce how to retrieve the past using historic map processing methods, and then how to reconstruct the past using the technologies like virtual reality, and then how to shape the future of cartography by leveraging generative AI for map making. So the context Lawrence has already introduced is an SF project for HistorReach, together with Iavag and Zeta Avi. And then it's also bounded with my doctoral dissertation named Deep Learning for Geographical Feature Extraction and Alignment from Heterogeneous Historical Maps. And we use two data sets in the study, the Siegfried maps, both scales at 25,000 and 50,000, and also old national maps that have to design variations like with or without relief shading. So now I would talk about the historical map processing. Previously, the processing is mainly semi-automated or required interactive manual processing. And currently, it's largely shifted to deep learning-based methods. And I have defined this workflow in my dissertation. So it consists of feature extraction that established a baseline deep learning model, and then transfer learning, that is to make the model generalizable among diverse maps, and then the spatial alignments, that is to make the extracted features aligned for further spatial temporal analysis. So now I will go into each individual component. So for feature extraction, there are some challenges different from images. Maps can have poor graphic quality and fuzzy definition of objects. This can lead to uncertainty in features. For example, for wetlands, as you can see on the left example, they don't have the clear boundary, and this can cause problem in segmenting the wetlands. And then on the left example, you can see the graphical defects from the storing, printing, and scanning. And to solve this problem, there are several solutions. The first solution I propose is to use uncertainty estimates. This is to model data-dependent uncertainty in deep learning. And data-dependent uncertainty means the uncertainty inherent in the original data or observations. So how to do it? It's actually, this method actually treats uncertainty as a learnable output. So if you see for the architecture here, beside the original prediction, the model would also output the uncertainty, for example, the bounds of the outlands, of the wetlands. And this can just be thought as a smart loss attenuation. So when the model is uncertain about the predictions, or it cannot make correct predictions, the model would try to produce a large uncertainty mask. So this is how the uncertainty is learned in a reinforced way. And here I show some results. So first, our model can capture uncertainty in object boundaries. In the first case, you can see the boundaries for normal objects like lakes in the pink, and also for the streams in the red. And in the second case, you can see the uncertainty can be captured at the objects with fuzzy boundaries like wetlands, including where it is intersected by a road in the middle. And the second scenario is the noise from drawing, producing, and scanning. In this example, you can see, despite the model can predict roughly correctly in the first case for the stream in the red, the model depicts a high uncertainty in the strokes that is unclear on the map. And also in the second example, you can see the high uncertainty is indicated at the printing or painting artifacts. The second scenario is unseen or rare designs. Here I show two special examples where the lakes have a slight tone of green that are different from normal designs that are usually blue. And you can see our model indicates a high uncertainty at those lakes. And based on this, we suggest some potential uses of uncertainty. So first, we can use it to filter out erroneous predictions and improve the final segmentation. And we can use it to detect the special symbols or designs. And third, we can use it to select reliable features for further spatial temporal analysis. And the second solution is that instead of modeling the uncertainty explicitly, we can elevate the uncertainty by using the spatial temporal context. For example, we can fuse the information from the map tiles that are spatially adjacent to the center tile, or from the temporal consecutive map sheets. For example, for the spatially adjacent map tiles, they can increase the spatial context that can aid better recognition. And for temporal consecutive map tiles, they probably have the maps that have better graphic quality that can also improve the segmentation. So that's the motivation of this work. Then we propose a novel neural network architecture that can fuse the information from both all these spatial temporal tiles. And we combine the strengths of different neural network architectures, like the normal convolutional neural networks, and also the transformers. That is another widely used architecture nowadays. Now I want to talk about transfer learning. As maps can have very diverse designs, like either foreground, like colors or textures, or also the background. For example, the third example has a slight shading effect. We know that a deep learning model is quite sensitive. Even a slight shift of distribution can make the model not able to generalize to the other data source. To solve this, we propose the first solution, that is to leverage the spatially occurring features between different sources, because maps are geo-referenced or geo-located. Then we can just simply pair the maps at the same location, and then we design a novel architecture to detect the co-occurring features between the different sources at the same location, or the changes between the features. And then we use the co-occurring features to supervise the model and to enable the transfer learning. And here you can see the result. The second line is a ground truth. That is what we are expecting. And the third line is a baseline model without the transfer learning at all. You can see the model fails for the lake in the second example. And also when the maps have relief shading effects, you can see the baseline model performs really poorly. And then our transfer learning approach can improve the segmentation very significantly. Yeah, then the second solution is also to use the style transfer approach. The last solution I mentioned needs geolocated data that can be paired together. But then the style transfer approach can also enable the transfer learning between maps that are data from different locations. And this is achieved by using generative adversarial networks, or GANs. So it's basically to translate the style from one source to another. And we propose a novel approach to address the semantic mismatches between different map sources. And here is the result. We can see a plausible translation from Siegfried maps to old national maps. And then we can train our model on the synthesized data and then apply to the real target data. The last one I want to show is spatial alignment. So now we can get the extracted features at different times, but those features are not necessarily aligned even after the maps are georeferenced consistently. Due to the difference in the producing or georeference errors, or also the other factors like deformation. On the left example, you can see the two map sheets from different years overlaid, and you can see the rows on the bottom right has larger distortion than the other features. And in a second scenario, you can also see the random shift of other elements like the toponyms. This can, like the red text in the middle, and this can hinder the estimation of the transformation between two different map sheets. To solve this, we use neural networks to estimate the per pixel correspondence and displacement between different maps. And then we apply the displacement field to warp the maps and to make the features aligned. And you can see our result on the right side. And our model is able to align the features with different misalignment degree, especially for the rows on the right. So now we have the extracted features. How can we reconstruct the past? Now I want to talk about another approach, historical landscape modeling in VR. So based on the map segmentation model and map alignment model, we can have the aligned features at different timestamps. And then we can also extract the height profile from the contour lines using methods like color-based segmentation or morphological operations. And then we use this to interpolate the historical digital elevation model and then paint the texture. And then we can visualize it in the virtual reality to allow for the immersive visualization and spatial temporal exploration. And this is a master thesis ongoing with Misha at our institute. And here I have a demo video for a small test region. So you can see with this VR approach, we can not only visualize the bird view overview of the whole landscape, we can also go into the landscape to get the immersive feeling in the past. So now I have talked enough about the past. I want to talk something about the future. So as you know, generative AI is now widely used to generate images instantly with user-specified prompts. And then we also explore the potential on the map making because it can be used for rapid map making, especially for disaster mapping, for example, and also automated map making to replace some manual or repetitive work, and accessible map making that can make this process accessible by the general public without the specific knowledge about the GIS and cartography. And also generative AI can be used to restore the historical map data if there's some missing map sheets. So how does this work? As you can see from the architecture, we use the stable diffusion model, and the specific version is called ControlNet. And we input the modern vector data, and we give the prompts like map in Siegfried style, and then we render the maps with our prompts. And our approach can generate a map in both modern styles and also the historical styles. As you can see in the first row for the generated map and the second row for the real map. And you can barely see the difference, especially for the contemporary data. And we asked the professional cartographers from the Atlas of Switzerland and also Swiss World Atlas within our institute to rank the similarity between the generated map and the real maps. And the score is from 0 to 5. 5 indicates the most similar. And you can see the modern map has really high similarity. And the historical maps have a lower similarity score, but still acceptable. So this shows the potential of our approach. And then to make this generative AI approach more accessible, we designed a web portal. As you can see on the left, you can upload the vector tiles and select different map styles. And on the right, you can play with your vector data. For example, you can add different features, or you remove certain features, and then you render the corresponding maps. So that's all I want to present today. So to conclude, today I give you a small journey through time. We talk about how to retrieve the past, use deep learning methods, especially for feature extraction, transfer learning, and spatial alignment. And we talk about how to reconstruct past to use the deep learning extraction results together with the contour line extraction and visualize them in the virtual reality to allow for the immersive visualization and spatial temporal exploration. And then I also talk about how to shape the future with the generative AI models for automated, rapid, and accessible map making, and also for historical map restoration. That's all my presentation. Thank you. I will go to next.
Thank you, Sidi. The next presentation will be video again from Xue Xia, and she is also dealing with a temporal series of maps, and I just start this presentation now.
Hello everyone, my name is Xue. I'm a doctoral student at the Institute of Cartography and Geoinformation at ETH Zurich. I'm very happy to share my research at the swisstopo Kolloquium. The title of my presentation is Map AI, Innovations in AI for Topologically Consistent, Low Resource, and Temporally Aligned Historical Map Processing. As the title suggests, my talk will cover three key topics in historical map processing: topological consistency, low resource training, and temporal alignment. Let's go through them one by one. First, I will discuss vectorizing historical maps while maintaining topological consistency. For those interested in more details, you can refer to this paper. Traditionally, historical map vectorization is performed through pixel-wise segmentation followed by vectorization. However, this approach often produces zigzagged, irregular vector outputs with significant topological errors, as shown in this figure. Correcting these errors requires tedious post-processing to refine the vectors. To overcome this challenge, we propose a pure vector-based workflow that integrates global line segmentation and instance contour detection to generate non-overlapping, regularized polygonal outputs. Let's take a closer look at the process using this figure. Line segments are defined by the coordinates of their two endpoints, while instance contours consist of a fixed number of ordered points outlining object boundaries. By matching line segments with detected instance contours, we assemble individual line segments at the correct sequence, ensuring the final contours remain simple and regular. This diagram illustrates the model architecture. We use a line transformer to predict line segments and a graph convolutional network to predict instance contours. The line segments and instance contours are then matched based on minimal distance, resulting in the final contour. Here is a real example illustrating the procedure. A shows the detected line segments. B presents the instance contours, which consists of ordered points. These points are matched with the detected line segments to determine the corresponding segments for each instance and their order, displayed in C, the matched line segments. Finally, D shows the final contour obtained by iteratively intersecting the matched line segments in the correct order. We compare the results of our proposed method with a conventional workflow that uses mask RCNN for instance segmentation, followed by vectorization. Our method produces simplified, non-overlapping polygonal instances, while the conventional workflow results in zigzag, misaligned boundaries. Additionally, our numerical evaluation shows that the proposed workflow achieves comparable accuracy while generating clean, intersection-free vector outputs. Having addressed the topological challenges, let's now move on to low-resource historical map processing. which means segmenting historical maps in scenarios with limited reference data. I will introduce three approaches: CNN-based template matching, self-supervised contrastive pre-training, and adapting vision foundation models. Classic template matching relies on comparing raw pixel values, making it highly sensitive to deformations such as scaling, rotation, illumination changes, and occlusion. In contrast, CNN-based template matching leverages deep features extracted by CNNs, creating a more robust feature space that better represents both the template and the target image, allowing for greater tolerance to variations. In this experiment, we used a single template as input to detect wetlands across different image map tiles, with slight variations in their appearance. To enhance feature extraction, we integrate domain-specific features from an autoencoder with generic features from a pre-trained VGG network. We then compute the cosine similarity between the deep features of the template and the target image. Once all wetland signatures are detected, we approximate their boundary hull to form the final detected boundary. The red boundary represents the generated boundary, and the green boundary indicates the ground truth. Our results demonstrate that CNN-based template matching can efficiently detect wetlands using just a single template. Currently, transformers have become the state-of-the-art compared to traditional template matching and CNNs. However, transformer models are typically data-hungry. To address this, we introduce a specialized pre-training strategy for historic map segmentation when using transformers. Since the same location appears with different styles across map series, we leverage this in a contrastive learning setting to pre-train a transformer encoder. Contrastive learning structures the latent space by pulling similar embeddings together and pushing these similar ones apart. We use image pairs from different map series, the Swiss Siegfried and Old National maps, to create correlated views. After pre-training, we fine-tune the segmentation head on a smaller labeled dataset. After contrastive pre-training, the pre-trained transformer encoder for the Siegfried map is combined with a segmentation head to form the network for downstream railway detection. Here, we adopt the swing U-net architecture. Here are the detection results. We reduce labeled training data from the full set to 1% for railway detection. Swing U-net with pre-training maintains consistent visual quality, while models without pre-training show discontinuities with limited data. Numerically, pre-trained swing U-net remains stable as data decreases, whereas non-pre-trained models degrade rapidly. Even with just 2.5% of labeled data for fine-tuning, the accuracy achieved is comparable to fully supervised approaches. These results highlight that contrastive pre-training effectively compensates for small labeled datasets. The third approach focuses on efficiently adapting vision foundation models. The rise of foundation models has introduced a new research paradigm for image segmentation. Instead of training domain-specific CNNs or transformers with extensive data, leveraging the zero-shot or few-shot capabilities of pre-trained foundation models represents a significant leap in scaling up segmentation models. In this work, we propose MapSem, an efficient adaptation of the vision foundation model SEM for historic map segmentation. The vanilla SEM requires manual prompt and struggles to recognize historical map features efficiently. In contrast, MapSem is fully automatic and demonstrates strong performance in segmenting historical maps. This figure shows the design of MapSem. We use DORA to embed domain-specific knowledge into the image encoder and introduce automatic prompt generation to remove manual prompts. The positional prompt is enhanced into a higher-level positional semantic prompt, and masked attention is introduced in the mask decoder. During fine-tuning, the image encoder is frozen, while the prompt encoder and mask decoder remain trainable. The proposed MapSem framework demonstrates strong performance across two distinct historical map segmentation tasks, railway and vineyard detection. To explore the resources needed to effectively fine-tune a foundation model for the downstream segmentation task, we progressively reduce the number of labeled training data to 10%, 1%, and even to just 10 tiles. Despite this reduction, MapSem maintains stable performance, accurately detecting railway features while preserving geometric continuity. We compare our framework against domain-specific models like UNet and state-of-the-art STEM-based models. When sufficient training data are available, domain-specific models like UNet continue to outperform fine-tuned foundation models. However, under limited training data conditions, fine-tuned foundation models prove to be a strong alternative for downstream segmentation tasks. Now, let's move on to the third topic, temporally aligned historical map processing. As a type of multi-temporal data, one persistent challenge with historical maps is linking geographic entities across diverse maps, a process known as geographic entity alignment. This figure illustrates the traditional approach to solve this problem. First, we extract vector entities from individual map sheets separately. Then, we link these extracted entities between two maps based on topological relations. In this work, we introduce a fresh perspective to solve this problem by conceptualizing historical maps as a unique form of videos. Compared to standard videos, historical maps can be thought of as extremely time-lapse videos, with intervals of several years between frames. Building on the idea of treating historical maps as videos, we propose a solution for geographical entity alignment using video instance segmentation. Traditionally, the approach involves a two-step process, first detecting entities within individual maps and then linking these entities across different maps using a post-processing step. However, with video instance segmentation, we can achieve simultaneous segmentation and association. This method significantly enhances the level of automation, eliminates the need for heuristic linking methods, thus improving generalizability. More specifically, we focus on linking building instances across different map sheets. To process the historical map sequence, we utilize mask-to-former VIS, which outputs a 3D volume containing linked building instances over time. To validate the performance of our proposed method, we conducted a comparison against the conventional two-step pipeline. In this baseline approach, we use mask RCNN for building instance detection, followed by the application of approximate topological relation to establish links between instances. Specifically, we utilize the approximately within relation, which is defined as applicable when the intersection area between two entities exceeds or equal to 60% of the area of the smaller entity. Once the instances are linked, they are assigned a shared instance ID. Here, we present some example results. The top row shows the output using the conventional two-step pipeline. The middle row shows the output of our proposed video method, and the bottom row displays the ground truth, focusing on the building in the lower right corner. We can observe slight distortions and displacements. The conventional method failed to associate the corresponding entities correctly, whereas mask-to-former VAS successfully tracks the object. From this, we can conclude that the video method exhibits greater tolerance towards displacements and shape alterations. Here are the numerical results. Mask-to-former VAS demonstrates superior performance, surpassing the conventional two-step method by a margin of 0.2 in F1 score. Therefore, we can conclude that video instance segmentation proves to be an innovative and efficient solution for geographic entity alignment. However, video format annotation data is costly to obtain. To address this, we propose a surprisingly simple method to generate synthetic videos to pre-train the VIS model. Our approach consists of two key steps. First, training an image detector to generate pseudo-masks. This requires only image-level annotations. Second, creating synthetic videos by duplicating images along with their pseudo-masks, enabling the generation of nearly unlimited synthetic historical map videos. For VAS model pre-training, experimental results show that this pre-training strategy significantly improves accuracy compared to the model without pre-training. In conclusion, we explored three major topics in historical map processing. To address the topological challenge, we proposed a pure vector-based method. To enable efficient segmentation with limited data, we introduced CNN-based template matching, contrastive pre-training, and foundation model adaptation. To achieve temporal alignment in historical maps, we formulate the problem at video instance segmentation. These are the approaches I have explored for historical map segmentation, and I hope you found them interesting. Thank you.
Okay, this was Xuya's presentation, and now we go over to Easy Chen. He will give us an outlook also to a certain extent to what we are also planning in the future. Please go ahead.
Yeah. So hello everyone, my name is ETH Chen and I'm currently a postdoc researcher in IKG group in ETH Zurich. And today I would like to give the title about the locking the past, enhancing access and usability of historical map. The main topic is basically like we are already getting enough data extracting from historical map, and now we are moving to the next step and how to help people or historians or even more stakeholders to use historical map resources more easily. And so the data source is mainly historical Swiss maps and contain Siegfried map and old Swiss national maps without and with release shading and without release shading. And so the Swiss map proposed multiple challenges where map have diverse design and scale and contain different type of symbolic representations. And as you can see from the first two images, the water depth of the blue lines is very similar to the strains in the second images, and also the lake features, and it's very similar to the strain features. And there are multiple challenges in the historical maps. As you can see, the first one is the printing and scanning artifact. As you can see, the blue color. And also there exist some printing errors. As you can see here, there are some gaps in the map features. And the last one is that the lake texture sometimes spread out, so it's very difficult sometimes to determine the boundary of the object. And for historical map research, there are mainly three main tasks. The first one is extracting map features, so-called vectorization process, that we extracting the semantic information from the map, from the historical maps. The second one is to extract the text from historical map, such as the street names and the topo names. The last one is also important. It's about the linking of object with the map alignment techniques, and this method will help us first we can easily compare the historical map and the current map easily to get the change, and it's also very important for measuring the change in land use, urban growth, and coastline shift. Also helping to check the place involved over time, and eventually this technique will help historians and planners to locate the lost place and interpret urban heritage accurately. And so far in the last few years, we are working very hard for extracting semantic meanings from the historical map. And this is the current state-of-the-art approach that we invented in our group, that we are using a lot of map information from the temporal information of the map and the spatial information of the maps to improve the segmentation result and to automate such process. And also we are working hard to extract the text information from the map. For example, left side you can see we extract many street names, and for the right side in Swiss map that we extract the topo names from the maps. This will and the text will be used as an anchor to link the geographical locations to meaning. And also for the last research we are doing, we are achieving the pixel level image alignment. As you can see, the left side is the previous map, and the right side is the map we are aligned. And as you can see, the text overhead, that is not changed, because that when we align map, we don't want to destroy and create the jitter in the text that can be further used by others. And as you can also see, the contour lines, our algorithms can match these contour lines and the map features accurately, as well as this example for the red arrow. And texts are not moving, and after the alignment, you still can read the text, and also our algorithms can align the text even for the tiny textures. So in this example, it's you can also see that the contour lines align and the roads are perfectly aligned. The angle represents the deformation directions, and so the algorithms is moving, making the deformation in this direction, and eventually the contour lines and the other feature, for example, the roads, are correctly aligned. So once we do all this step, feature extraction, vectorization, and the text extraction, and aligning the historical map, what the next step is that we're trying to build so-called knowledge graph. That the knowledge graph is trying to link everything together in spatial and temporal manner. And as you can see, that we are creating this so-called graph that will connect all the map features in one map, and also in a temporal manner. To get this spatial graph, we can first vectorization the map and the digitization the map. And for the temporal graph, we align the instance of the map together, and to match the instances with the same semantic meanings. And since now we already put the map features in this so-called knowledge graph, and we can also involve more geographical informations and adding in this graph to enhancing its geographical properties. For example, that we can add the topo names, and we can add more data, for example, the census data into this graph. And this graph contains a lot of information and based on the geographical entity. And now we have a geographical knowledge graph in IKG in Zurich. And however, there are so many knowledge graphs that, for example, the finance data knowledge graph and the census data knowledge graph that distributed among in Switzerland. However, if you want to have a connection of the information, and you want to integrate all the informations and to try to understand the complex questions, sometimes it's difficult, because those knowledge graphs are not connected with each other. That exhibit a limitation that knowledge graph have different structures. For example, the geographical knowledge graph have very different structure compared with the census knowledge graph. And to merging this knowledge graph into a very big knowledge base, it's very difficult because they are built with various applications, and this leads to that knowledge graph are not connected. So it means that the knowledge are not connected. So for example, in each knowledge graph, based on its complexities, and in each lab, they have a very specific person to maintain this specific knowledge graph. And so for the stakeholder, if they want to ask a question about like how did changes in river body influence the population of Bargen from 1916 to 1920, this question involves the geographical information, for example, the river bodies that need some information from historical map, and the populations, for example, the census from the census knowledge graph. In this case, to answer this question, we need to gather a lot of information from different various resources. So the person who asks the question have to first go to the geographical knowledge graph, and then he need to go to the finance data, for example, or even further go to census data to gather all the informations. And at the same time, he need to know how to query the information from the knowledge graph. And this database information and knowledge graph information are sometimes difficult to learn. So this is super time consuming, and problem occur when knowledge graph are not always accessible, because you need to contact to a specific person in order to understand the structure in their knowledge graph. So, and as you can see here, the constructed knowledge graph, it's very abstract and very difficult to understand by an amateur. So now we want to solve this problem by trying not to go to the person, but using a large language model that can be used to connect to very different knowledge graph that is able to help the person when they ask the question in plain text, for example, in this question, and the large language model can answer the plain text to you and to give you a more direct explanations for your questions. And why this large language model is good for us? First, it's very easy to access because you can use natural language instead of complex query and a lot of database and knowledge graph knowledge. And it's also across knowledge graph linking. It can also help to connect information across different knowledge graph, and you don't need to learn any knowledge graph information. And the last one is it will help automatically manage different knowledge graph and also for updating and context and to create such complex relationship between different knowledge graph. So this is our next step moving further to helping the people to access the information that we extracted from our historical map. And by building this knowledge graph with a large language model, first we can do, it's good for knowledge graph construction that can extract the entities and relations from unstructured text to create and enrich the relation of the knowledge graph. And also, you don't need to learn any database or other knowledge graph knowledge. You can just asking natural language as a queries, and the language model will answer you in the plain text in a easier understandable format. Also, the knowledge graph can help us to complete the informations to predicting the missing informations in the several knowledge graph and helping you to extract and abstracting the information you needed based on your question. And it's also it's good for summarization the knowledge, and sometimes when your knowledge graph has some problems or logical flaw, then the large language model can detect those errors and spot inconsistency, and only using only provides you the information that you will need based on this system. And this is all my presentation, and thank you very much.
Okay, thank you, Easy. Do you have my last presentation also?
After this,
Okay.
I think we have to wrap it up.
Okay, so then we're at the end of the presentation. Thank you.
So, thank you very much for this insight into your work at ETH on how you deal with historical maps from a Digitisation. Oh, yeah. Funktioniert. Thank you very much for your presentations and for the insight into your work at ETH on how you deal with historical maps from a digitization standpoint. As a historian, I of course hope that the things you presented last, Yeezy, don't replace my work, which is of course always the question with AI, how it changes the way we think and the way we deal with information and how we obtain it. It's very impressive what you do with the historical maps and how you juggle them and how you play around with them as well. And before we move on, maybe to some questions, I want to point out 2 next dates in the calendar of swisstopo. That's the next Kolloquium, which will deal with the news from the Swiss Kataster, and very important, the day of the open door on 24th of May. That's a Saturday, when everyone is invited to come here and to look at what we do here at swisstopo in all parts of the office. So thanks again, and maybe there are some questions. Jawohl, Lea.
I wanted to ask whether the maps you used, they were in your institute, were they your own? The original paper maps? Siegfried?
No, we were mainly using the swisstopo maps, which are available.
Which were
yeah.
scanned already here?
Yes.
Okay.
Yes.
Thank you.
And when you approached these maps, did you also use materials from other sources like archives where they write about the maps or the sign explanations, etc.? Did this play any role in training the AI? Because I've seen that you extracted the meaning of the symbols, if I understood that correctly, from running the AI over it. Or did you already tell the AI from the beginning, this is that, like the sign explanation tells us?
Well, we were also using that part. So, for instance, when we produce synthetic data to improve the training of the model. So there was this presentation by Chenjing. So the one just after my intro presentation, she was actually using TLM data and applied the symbolization of the Siegfried data on the TLM data by creating thereby a synthetic Siegfried map based on TLM data. And we used that to have more training data because we didn't have enough training data from the historical sources. So that's one example where we actually used additional information like the Zeichenerklärung from the Siegfried map in that case. Yes.
Okay, so if there are no further questions, we close this colloquium. Many thanks to everyone who helped organizing it, and especially thanks to Lorenz, Yeezy and Sidi, and have a great day.